Aren't you proud of me? You know, they were doing that California rolls covered with I went there both days that they were taking them out, and I could eat them just
No, it didn't feel that long.
By the way, I applied for a job at Roush.
Really?
You're not in a good mood if you want to.
No,
It was like nice
On
one.
Thursday.
yeah, well, I don't know. There's some good, like it was great, great weekend.
And then
Then,
some
but then
bad.
some like one day where I just like worked.
Yeah.
Yeah, me too. I pretty much save all my homework all the time for the last day of the weekend, so it's Sunday, or the 3-day weekend, it's Monday. It's always quiet. I don't know, maybe we're... Let's see. Friday I do something for the table.
So I'll click the two things at once, by the way, you don't have to. All right, so I am collecting the lab and also the problem from chapter 9 was number 105. Make sure your name is on each, please. Please pass it to the right-hand side as always. Make sure your name is on the...
What's the matter with you?
Very good. All right, please take out your notes. Take a look here at the agenda board. We're actually kind of down to the wire here for chapter 9. We're just going to today cover the last topic, which is brief. Then after that, we'll take a look at today's mini lab, which will actually take us through the remainder of the period. But as you can see, the next exam is on the horizon. Now today's Tuesday. On Thursday of this week, we'll review for the next exam, which is next Monday. That's Monday the 23rd, so make a note of that. All right, let's go ahead and get to our last topic here for chapter 9. It's a brief look at what is called impulse. Impulse has to do with the details of one of the things that we skipped over when doing a lot of the problems that we saw in chapter 9 on explosions and collisions. When we looked at those types of problems, we were only concerned with what happened before the collision, for example, and then what happened after the collision. We actually really didn't say all that much about what happened during the collision itself. That is, a look at the internal forces that one object exerts upon the other. That's what we examined here briefly with this topic called impulse. So we're going to just take a brief look at the internal forces that occur between objects during an explosion or collision. Now I'll demonstrate it on my desk in just a few moments using my carts, so I'm going to treat it as an example here as a collision situation. So just imagine, for example, some sort of one-dimensional elastic collision where the carts just bounce off each other. Now previously we would have described such a situation in the following way. We would have said, all right, well, before the collision, the first cart, mass m1, has initial velocity v1 naught. Second cart, mass m2, has initial velocity v2 naught. They bounce off of each other. Cart number 1 has a v1 B1 final, card number 2 is B2 final, and then we would have plowed through all of our algebra to solve for those two velocity vectors. And now we're concerned with taking a look at here at what happens for the moment or two, if you will, during the collision. So now, during the collision, let's picture it the following way. I'll draw it nice and large here for clarity. We have M1 and M2 like so, and they exert internal forces on one another. So then therefore, for example, there is a force on 2 due to 1. And then from Newton's third law, of course, there's an equal and opposite reaction. That is, there is a force on 1 due to 2. Okay, now the mathematical behavior of these forces is actually pretty easy to describe. The easiest way to visualize it is with these elastic bands, even though the collision itself here occurs very quickly. A few hundredths, maybe even a few thousandths of a second like so. But basically the mathematical behavior of these internal forces is as follows. So the force between the objects themselves, the force that say one exerts on the other, goes very rapidly from a value of 0 at the moment of first contact to a maximum value as the springs here compress their maximum amount. And then just as rapidly, the force will then go from that maximum value back down to 0 once again as the carts separate from each other. This occurs very obviously between the elastic bands here, between the carts themselves, but this actually also occurs with seemingly very rigid objects. During the collision itself, the objects actually noticeably deform, much like springs. And very rapidly, the force goes from a value of 0 to a maximum value, and then back down to 0 once again as the objects separate from each other. Under the right conditions, you could actually photograph this, for example, with high-speed photography. Let me show you an example of this. This photograph right there. This right here is a high-speed photograph, so it means many frames of photographs are taken per second. This right here is a high-speed photograph of essentially the moment, if you will, between what happens when a baseball and a baseball bat collide. And you can see that very noticeably the baseball is flattened out, is deformed, much like, for example, the elastic bands here on the carts. And then it's also a little bit hard to see here, but the bat itself, which is an aluminum bat in this case, actually noticeably deforms as well. So seemingly very rigid objects kind of act like these elastic bands here between the carts when some sort of high-speed collision takes place. The collision itself in this manner is actually very easy to model. The way that we model the collision is a very specific type of graph. What we do is we graph the force, and it doesn't matter which one, by the way, because they're the same by Newton's third law, as a function of time. When you construct this graph, there's a very characteristic curve that is traced out by one of these internal forces. It basically looks like a really skinny spike, if you will. That is, the force goes from 0 very rapidly up to a maximum value as the carts compress together, and then back down to 0 once again as they separate. So right here is a really small time interval over which the collision occurs. And then the height of this spike right here is basically the maximum value of the force that occurs between the objects as they collide together, much like the baseball and the bat, for example. Now, how do we mathematically describe this? Well, it actually just comes directly out of Newton's second law. So here's what I mean. Now, I'm not going to write Newton's second law here as F equals ma. Instead, I'm going to write it in its more general form that we saw in the Mechanical Universe episode on momentum last week. Remember, its more general form that the sum of the forces is equal to the change in the momentum of an object with respect to time. Watch what happens if I just take Newton's second law there and move the time interval up to the left-hand side and then integrate. Okay, now before I get to the left-hand side here, let me just go ahead and integrate the right-hand side. The right-hand side is just the change in the momentum of one of the carts up on the top board from before to after the collision. But now specifically take a look at this quantity here on the left-hand side. What is the left-hand side describing about this curve, which is a plot of force as a function of time? Anybody tell me? Remember, what does an integral always describe?
The area.
Yeah, it's the area underneath the curve. It's the area of this spike. The area of this spike right here is the left-hand side of the expression. The left-hand side of the expression is referred to as impulse. It's a new quantity for our purposes. The impulse is given the letter capital J. Strictly speaking, it's basically the area underneath this curve. Now the curve itself here, this spike, could actually be described precisely mathematically. It's an example of a type of function. It's called a Lorentzian. It's basically a really skinny bell-shaped curve, but we're just going to approximate the curve here without worrying about some complicated function in the following way. We're going to approximate this curve as basically a rectangle. So as an approximation, think of the graph in the following manner. So the force as a function of time that one cart exerts upon the other as they collide could be kind of summarized here or approximated as just a skinny rectangle, like so, where the base of the rectangle is a short time interval, delta t, over which the collision occurs. And then strictly speaking here, the height of the rectangle is not the maximum value of the force. Instead, it's actually the average force that occurs when one object collides with the other. So this right here is just an F bar. It's the average force. Now the left-hand side here, this new quantity, the impulse, that's still the area underneath this curve. And in this case, it's just base times height. So the base times height then, which gives us the area of this rectangle, is now just the following. The height is the average force multiplied by the base, and that then gives us on the right-hand side of the expression the change in the momentum. Okay, now here's why we bother to define this quantity. Not only, number one, is it descriptive of this graph, the force as a function of time that occurs as the objects collide together, but it's actually also mathematically easy to determine because it's equal to just the change in the motion or the change in the momentum of one of the objects. So if I'm talking about the impulse imparted, as we say, or delivered to one of the objects, say number one, it's nothing more than its final momentum at 1v1 final minus its initial at 1v1 naught. So the quantity itself is easy to determine for this reason. The hard part about all of this is the time interval. How do you measure the time interval of the collision itself, for example, when it occurs between these carts at just a few hundredths or a few thousandths of a second? Well, you have to do something like this. You basically have to photograph the collision by using high-speed photography. Once you do that, you can then measure the time interval itself. Then you can get an expression here or a number for the amount of force that occurs as the objects collide together. But if you can't do that, in order to at least describe the force, we define this quantity called impulse, which is easy to find. It's basically just the change in the momentum of the object itself. Okay, now we do have new units here to worry about because it is a new quantity for us. Okay, the units of impulse, the left-hand side of the expression here, is basically the same as the units of momentum, but the units of momentum are not really descriptive of the force itself. Instead, we write the units here of impulse as force times time. It's just newtons multiplied by seconds, like so. Okay, now mathematically and problem-wise, we're just going to keep this really simple and straightforward, nothing too complicated, just a brief look at what happens as objects collide together. I'm actually going to use baseball here as a nice example for a numerical example. That's this. Okay, now as you start to read through the example here, the questions, by the way, are on the next page. All the numbers here are realistic, that is, with respect to baseball. Okay, in the major leagues, for example, there is a standard mass of the baseball. It's 150 grams. Okay, then the baseball is initially traveling at 40 meters per second the instant before the collision with the bat. 40 meters per second is a pretty good clip. That kind of corresponds to a good fastball. And then the ball leaves the bat in the opposite direction with a speed the instant after the collision of 60 meters per second. That is once again a realistic number. So this is basically when you have a really good solid collision that occurs between the baseball and the bat when the baseball is initially thrown as a fastball.
So what's the question?
So the question, and I just gave you enough time to copy down all those info. The question is in two parts. First, find the impulse imparted to the ball. That's the terminology that's used. As we'll see, this is really easy to find. And then after that, we'll calculate the average force that the bat exerts upon the ball for part B. Sometimes we use the terminology the impulse delivered to the ball. And we'll assume that all the velocities here at the baseball before and after collision are horizontal, just to keep things simple, nothing too detailed. All right, so let's picture the problem the following way. So right here is the baseball itself. It has a mass of 150 grams. Of course, we have to convert this into kilograms like so. And then its initial velocity, the instant before the collision, V naught, is 40 meters per second in this direction. Okay, and then it collides with the bat. Okay, I'm just going to kind of draw the head of the bat as if it was pointed straight at us, like so. And then right here is the baseball in collision. So this is the head of the bat pointed straight at us, like so. And then here's the baseball. So during the collision itself, there's an average amount of force that's exerted upon the baseball due to the bat, like so. So there's an average force on the ball due to the bat. Okay, we'll determine what this is, by the way, at the end of the problem. And then the instant after the collision, the baseball is just moving in the opposite direction with a V final vector like so. But this is a vector quantity. We just have to make sure we keep track of negative signs correctly. So its velocity in the opposite direction would be negative 60 meters per second the instant after the collision. Okay, now part A of the problem is to find the impulse imparted, as we say, to the ball. So I'll call this capital J on the ball. This is easy to find because it's nothing more than the change in the momentum of the ball itself. Now, we're not doing a conservation problem here or anything like that. We're just looking at one of the objects, in this case, the ball. So the change in the momentum of the ball is equal to the impulse. This is easy to find. It's just the final momentum, mv final minus the initial mv naught. We can go ahead and just plug in and get our answer. Easy enough. So as I said earlier while lecturing, this is easy to find. So I have 0.15 times then negative 60. Just got to watch your negative sign when doing this. Minus 0.15 times 40, and that ends up being negative 15 Newton seconds. Okay, impulse, which is basically force times time, is a vector quantity. The negative sign means that this vector here points to the left. Okay, easy enough. The hard part of all of this, unless you can measure the time directly, is to calculate the force. But if you can find the time somehow by measuring it, as I said, would say high-speed photography, then we can also find the force itself, which is at this point is easy to do. So then we find the average force in the following way. Okay, the impulse on the ball is basically force times time. It's the average amount of force exerted upon the ball multiplied by the time interval, and as you can see from the problem, the time interval is really short. 5 milliseconds is only 5/1000ths of a second. Usually when you have a high-speed collision between very rigid objects, the total amount of time over which the collision occurs is just a few thousandths of a second. So the delta t here is given, this is measured, at 5 times 10 to the minus 3 seconds, that's 5/1000ths of a second. Okay, then all I have to do is take the impulse that we just found and divide it by the time interval and I have the average force. There's not much to this. As I said, we're just taking a brief look at this topic and nothing more. And then therefore, I end up with negative 15 Newton seconds, and then I divide out from that, though, 5/1000ths of a second. So because the time interval is quite short, this means that the force is going to actually be pretty large. It's negative 3,000 newtons. The negative sign means that it just points to the left-hand side. Okay, 3,000 newtons, just to kind of give you a basic idea of that number, if I just quickly convert it into pounds for us, that's about 675 pounds of force. These are fairly typical numbers for a situation such as this. Okay? Yeah?
Is it typical for when you hit the ball to be moving faster than when it was thrown?
Yeah, because what you're doing by swinging at the ball, and you're delivering energy to it. You're transferring some of your own kinetic energy to that ball.
But don't you have to change the direction of it too?
Yeah, we're ignoring that detail here. So we'll just assume it just rebounds off the bat like that horizontally. Just keep it easy to picture. All right, good enough. Minimize all this. And then let's get to today's Community Lab. All right, where is today's Community Lab? It's buried on my desk somewhere.
Should I do on that?
Yeah, I'll grab it in just a sec.